Thanks for the flowery introduction, Eli. So we're going to go from the highest level system type considerations all the way back down now to the very most fundamental considerations. We sort of did this in the construction of the program. Wasn't our intention, but because of a variety of constraints and so forth, we will now go for a period of time in the program into the device level and some of the even more fundamental, most fundamental concepts in electronic and magnetic devices, and then on into photonics, and then wrap up towards the end of the day at the highest level of the system. So, you don't hear me? Really? Yeah. Okay. So what I'm going to do is talk about concepts, and I specifically use the word concepts here in this talk because I'm going to show you elements of information technologies, but we're still, this is the most exploratory, farthest out the type of technology work that you're going to hear about during this day and a half symposium. And I would like to characterize the concept of magnetic computing as very much in the exploratory phase. We're looking at phenomena and elements and trying to put together the piece parts that we could eventually use to construct a full-blown processing technology. But what I'm going to show you are some of the fundamental piece parts in this talk. So first of all, let me lay some background here. When we're in this regime of trying to approach the very fundamental limits of energy dissipation in computing, we're doing what I like to call counting KTs, right? And the famous work, and we've seen photographs a couple of times, even this morning at the system level, of the pioneers John von Neumann and Rolf Landauer, who in work way back in the 60s showed on the basis of very fundamental considerations of thermodynamics that and statistical mechanics that in any logic operation there was, on the basis of information entropy, a minimum energy dissipation of kT log 2. And actually, this has since been generalized. If you want to have an operation with a low error probability, you have to dissipate more energy by the log of the error rate. Now, where do we stand today in our existing MOSFET switches? Well, the way we switch a MOSFET is to charge up the capacitance of the gate. That takes an energy half CV squared. There are n electrons. Electrons come in, quantized packages. There are n of them with charge Q on the capacitor, charged up to voltage V to get that CV squared. Now, when this serves as the gate of a MOSFET, the voltage that we need to switch the MOSFET with a certain on-off ratio, as we've heard a lot about in the last yesterday, is KT over Q times the log of the on-off ratio. Right? So we need enough voltage on the gate of the MOSFET to swing it by the voltage swing. And so the energy that it takes to run a thermally activated MOSFET switch is NKT, where N is the number of electrons. Now, this is a result that was derived by, and I forgot to mention, this talk is a collaboration between myself and Saif Salahuddin here at Berkeley. And this is from an earlier paper of Salahuddin, this result. And while it's not as rigorously provable at the level of Landauer and von Neumann's analysis, in general, what's pretty well accepted in the community is that for switching, if we're switching using n particles for the switch, we typically are looking at more like NKT, where n is the number of particles. And the number of electrons on your typical MOSFET, could be in the range of 10 to the 6, as high as 10 to the 6. And Of course, with now what about TFETs, you ask? How does that help? If we can increase the subthreshold slope, we somehow seem to beat this number down, and that is true and consistent with this argument. And one of the interesting things about TFETs, and I think this point was made in a couple of the talks yesterday, is that by squeezing the band edges together with the density of state switch, there's an effective clipping or filtering of the Boltzmann energy distribution, the thermal tail, the Boltzmann energy distribution. So in a properly designed TFET, what you really are doing is effectively lowering the temperature of the electrons that are being injected into the channel. And since this is really the number of electrons in the channel that we're talking about, that's where you can really get some headway with TFET. So it's all kind of consistent. Now, I want to talk about magnets, right? So a small nanomagnet, a single domain nanomagnet, sort of looks rectangular like this. If we arrange a magnetic thin film into a rectangle like this, we get what's called shape anisotropy. The magnetization of such a magnet prefers to be aligned along the long axis of the magnet so that we can encode a binary bit, magnetization pointing down. We could call that a 1, magnetization pointing up. We could call that a 0. When the magnetization points along this direction, we call that the hard axis. That's a high energy state. This is a plot of energy versus the angle of the orientation of the magnetization relative to the long axis of the magnet or the easy axis. That's a higher energy state. If we put the magnet up here on the top of this energy barrier, it can be very sensitive and take very little energy or very little force to flip one way or the other. And that gives us some interesting possibilities in using nanomagnets. Now, back to this argument about counting KTs. The interesting thing about a nanomagnet is that in a single domain ferromagnet, the N spins are tightly locked together by exchange interaction. And so, in fact, in a nanomagnet, there are actually only 2 degrees of freedom. And the expectation is that the energy, the minimum energy that it takes to erase a nanomagnet bit would be not N, where N is the number of spins in the magnet, but only KT. So 1 KT instead of N KT. Now, an interesting point about the nanomagnet, here is a magnetic hysteresis curve for a nanomagnet, and note the very steep characteristic of the switching. So it's also a very steep sort of threshold device. And that's an interesting parallel to the notion of having very steep switching and low energy dissipation. And in general, this type of collective behavior where we are flipping a large number of particles or somehow manipulating a large number of particles, we find a commonality. For instance, in the mechanical devices that we heard about, the NEMS device, we're moving a cantilever with also a very large number of atoms. We're physically moving all those atoms, but they are collectively locked together and show a very similar kind of switching characteristic, in fact. Ferroelectric materials also have a similar property of hysteresis, very steep switching, collective behavior. These collective systems, unfortunately, seem to have the common feature that because they are stiffer, there is some sense a much larger net effective mass, and so they do tend to operate more slowly. It takes more time to flip a nanomagnet than it does to charge a very small capacitor. So there seemed to be a trade-off, although how fundamental that is still yet to be decided. And this slide, this conclusion about a 1 KT for a magnet flip is a subject of a paper of Salahuddin's from 2007. And of course, as I'll show you, Bennett actually analyzed nanomagnets in his paper following up on the work of his mentor Landauer at IBM in the early 80s. And what Bennett actually analyzed as a specific physical implementation of the Landauer principle, a nanomagnet. And this is a figure taken from his paper from 1982 on the thermodynamics of information. And I won't take you through this in detail, but basically what he analyzed was the case of a nanomagnet subjected to applied magnetic fields to polarize it along its hard axis, put it at the top of that barrier when the two states on either side of the barrier become degenerate, and then with a small magnetic field tip that magnet to a specific state, and he analyzed this theoretically to come up with this 1 kT log 2 for the nanomagnet. Now, a clever graduate student in my group, Brian Lamson, took a look at this and said, you know what, this was a Gedanken experiment by Bennett, but you know what, we now have the capability to make these nanomagnets and to measure them, and so, you know, we could actually do Bennett's experiment. And this was a very interesting idea because while there's all this elegant theory, nobody has ever actually done a satisfactory experiment to make direct experimental contact with Landauer's principle, at least to my knowledge and satisfaction. So we said, you know, maybe we could actually do an experiment to check this. And this shows the sequence of application of magnetic fields. So we apply a magnetic field along the hard axis and another component along the easy axis in this sequence, which is in fact exactly Bennett's prescription. The question is, well, how do you do the experiment? Well, this is a set of simulations that Lamson did in order to address that question. And what he proposes, well, if we could measure the magnetization state of one single nanomagnet as we apply the magnetic fields in the x and y direction, these would be the hysteresis loops that we would measure, that we would expect to see. And he did this by micromagnetic simulation and put temperature into the system. There's a well-established and well-calibrated micromagnetic simulator called UMF that was developed at NIST, which allows the inclusion of thermal fluctuations. And as you measure the hysteresis loop in the x direction and in the y direction, as the magnet goes downhill, it gives back energy. You're putting energy in to polarize the magnet along the hard axis. The net energy dissipation in the magnet is the difference between the areas of these two hysteresis loops. And in a Monte Carlo simulation, what Brian showed is that the expected value of the energy dissipation would be exactly kT log 2, and there would be a width to it. There would be some fluctuation. So in fact, you can cheat Landauer's principle half the time statistically. And as a function of temperature, here's the kT log 2 line. The simulation follows, except when he went to very, very low temperatures. And the deviation here is because we didn't allow we didn't run the experiment slow enough to be in the fully adiabatic regime during the whole time. So you get some deviation there. But at room temperature and modest temperatures, the simulation shows that the experiment should work. So this was a nice result that actually just recently appeared in PhysRev Letters. Now, how about doing the experiment? So we're approaching two different ways of doing this experiment, but one of them is to use a tunneling magnetoresistance sensor, which is a very sensitive sensor of the magnetization of the free layer in a magnetic heterostructure stack. And so here's progress on the experiment. We haven't fully completed this study, but here's an example of the data. Here's what the simulation shows for the y-axis hysteresis loop. And using the TMR sensor, applying magnetic fields according to the prescription, here's the measured magnetization loop for this particular nanomagnet. So whereas the energy loop area for this loop is about 14 kT, he actually measured 13 with some error on the order of a few. And so at least in this first cut, we're making some pretty good progress on being able to investigate experimentally this regime. Now, you might object, and rightly so, that, well, wait a minute, you're flipping these magnets with a magnetic field, and you haven't taken into account the energy to apply that magnetic field, and that would be quite correct. And generating magnetic field is kind of inefficient, right? You have to put current through wires, you generate the magnetic field through space, and it's very challenging and difficult to make that efficient. But, well, actually, I'll address that in a second. I just wanted to show very quickly, in simulation, what Brian did was went the next step and put together a nanomagnetic logic gate. This is called a majority logic gate. And what he also showed, again, by explicit micromagnetic simulation, was that indeed we could also verify Bennett's proposition, which was that if you operate in the right order, that is, if you don't destroy the information from the inputs before you destroy the information at the output, that you could run this in the Bennett mode of reversible logic. And so the energy dissipation that he calculates, that's, again, leaving out the applied energy to generate the magnetic fields, but the intrinsic energy dissipation in this array of magnets would grow dramatically as the near neighbor coupling energy grows. But if you operate in the reversible regime, he explicitly found that you could dissipate zero energy. So that's kind of interesting. It's a big challenge to figure out architecturally how you would actually build a processor that could operate in this mode. But we're in the game of trying to investigate some of these fundamentals. It looks like that these nanomagnets could be at least a potential way to implement reversible computing. Now, back to the problem of how do we actuate these magnets without spending a ton of energy to generate external magnetic fields. And there's some really interesting progress from the material science community on materials which are referred to as magnetoelectrics. What a magnetoelectric material is a material which has at least two what they call ferroic orders. That is, for example, a magnetism and also ferroelectricity. And there's a material, bismuth iron oxide, BFO, which is being actively researched by my collaborator here in material science at Berkeley, Ramamurthy Ramesh. And this is a material which is ferroelectric and anti-ferromagnetic. But it has these two coupled properties at room temperature. And the anti-ferromagnetism is tightly coupled to the ferroelectricity. If you flip the ferroelectricity of this material just by the application of an electric field, you can actuate a magnet which is exchange coupled to the BFO. So the anti-ferromagnetism flips, and an exchange coupled magnet can then be flipped by its exchange coupling to the BFO. There's another way of doing this with piezoelectrics and magnetostriction, but in the interest of time, I won't walk you all the way through that. But the beauty here is that we could potentially actuate magnets purely by the application of electric field across what this material is an insulator. It's a ferroelectric, but there's no direct current that flows. We're basically charging up a capacitor again. And this is being actively researched for memory, and what I want to talk about is its potential use for magnetic logic. Well, just to show you that the progress on this has been dramatic in the last couple of years, this is data from Ramesh's group in which he's got a cobalt platinum nanomagnet sitting on top of a layer of about 200 nanometers of BFO with an electric field applied in the transverse direction by these two electrodes. And what this data shows, this is called anisotropic magnetoresistance. Without going into a detailed explanation of this data, what we're plotting is resistance measured through the magnet as a function of the rotation of this entire structure within a weak applied magnetic field. And what it shows is the phase of this cosine-like behavior is an indication of what the magnetization direction is of the magnet. So with the application of an electric field of 130 kilovolt per centimeter, the phase flips by 180 degrees, demonstrating conclusively that the magnetization of this nanomagnet flipped by 180 degrees. So we actually have this working. There's been more recent results in which the electric field is applied not in the in-plane direction, but the out-of-plane direction. And they've unpublished data. This work is in press. The vertical field data is in preparation. And applying the field across the thickness of the film, of course, reduces the voltage required dramatically. So on the basis of this data, we can make projections, and the energy dissipated here is the energy to charge up that nanoscale capacitance. And, well, to get to the bottom line, if we could scale this to about 20 by 20 nanometer size nanomagnets and about 3 nanometer thick BFO film, which appears to be at least within reason, that would get the switching energy, the actuation energy down to in the attojoule regime. And so what about a logic device? Well, here's a representation of 3 different magnetic logic devices that are being researched at various laboratories. All spin logic is a scheme that involves nanomagnets coupled to a conductor in which the spins are the spin accumulation occurs by spin injection, and I'll show you a little bit more about this phenomenon. Nanomagnetic logic is one in which the nanomagnets interact via their stray dipole magnetic field coupling. Spin wave logic is another scheme where spin waves are injected through a metal that's coupled, again, exchange coupled to the nanomagnets. All 3 of these involve nanomagnets and would benefit from the actuation available by magnetoelectric coupling. Now, just a few words on interconnect. If we're flipping magnets, it'd be nice to be able to communicate information between those magnets without having to do electrical communication. And the idea here is that using a magnet and a very small current in which we could inject spins into a normal conductor, create spin accumulation. Those spins would diffuse and be able to flip another magnet. So as a coupling mechanism with some ability to communicate over at least local interconnect-like distances, we might be able to communicate. Because spins are very weakly coupled to the thermal excitations in the metal, the dissipation here could be rather low, and you have protection from thermal fluctuations. This type of non-local spin transfer has been demonstrated experimentally by a group in Japan, published in 2008. I won't walk you through the details of this, but basically by injecting current from one magnet into a normal conductor, where the electrical current goes this way, the net spin accumulation in the normal conductor diffuses the opposite direction. And in this experiment, they demonstrated conclusively that the second magnet could be, in fact, flipped. Now, if we could use magnetoelectric actuation, put a few attojoules of energy into that detector magnet to put it on the hard axis, it would be even more sensitive. And calculations by Salahuddin show that an excess net accumulation under the detector magnet of only literally a few Bohr magnetons can flip that magnet. So the energy dissipation in the amount of current that's to inject enough spins into this end of the wire at the transmitter side would be down in the zeptojoule range, with only a few attojoules necessary to pump a little bit of energy into the receiver magnet to make it sensitive enough to flip with this amount of input energy. So that looks pretty promising, and Salahuddin's group is actively working on trying to demonstrate that. What's the distances you might be able to communicate over? Well, spin diffusion lengths in copper are on the order of half a micron. Silicon could be as much as 10 microns. Graphene has been actively been looked at as a spin channel recently. It's got a spin diffusion length of about 2 microns, and its advantage is that the speed of operation of this interconnect could be ballistic, in other words, non-diffusive, over a distance that's not related to the spin diffusion length, but by the momentum transfer, momentum mean free path, which in graphene is a very high mobility material, could be quite long, also on the order of a couple of microns. And so we could probably imagine a spin-based interconnect with at least an interconnect length in the neighborhood of 10 microns or so. Now, I just want to quickly show you one little trick that we came up with in my group for helping with this clocking. As I described, clocking involves putting a magnet up at the top of the energy barrier to make it extra sensitive. But of course, at that point, it's extremely sensitive as well to thermal fluctuations and very error prone. If you could somehow create a trick of magnetic anisotropy and create a little bit of an energy minimum at the top of that barrier by a more sophisticated anisotropy, that would really help. And we came up with one. If you monkey around with the shape of a rectangular nanomagnet and put this concavity in here, what happens is you introduce exactly what I was talking about, some remanence or some easy axis component along the short direction, and this actually shows what the hysteresis loop looks like. Note that steep, this is micromagnetic simulation. Note the steep switching threshold for putting the magnet right at the top of the barrier there. That is represented in this magnetic susceptibility polar diagram as these lobes. So in the normal rectangular nanomagnet, we just have an easy axis up and down. Here we've introduced a little bit of easy axis along the short direction. And in fact, we've been able to demonstrate experimentally that this works. And here is some data that demonstrates the metastability of these concave nanomagnets. As we increase the concavity depth, the metastability along the hard axis becomes so strong that the magnets don't ever flip. They stay locked up. With a little bit less, the magnets couple by their dipole field, and that's represented by this magnetization, this it's an X-ray magnetic microscope at the synchrotron, and we can see that the magnets flipped and coupled strongly by these magnetic images. So let me just wrap up with some prospects for magnetic computing. So what I've tried to show you is that at least the intrinsic energy dissipation for flipping magnets can reach the ultimate limits. We've got this innovative new mechanism for controlling magnetism directly using an electric field with these exciting new multiferroic materials. At the moment, it looks like we could project that these might scale into the attojoule range. So that's pretty interesting. I mean, doesn't quite get us to the KT log 2 regime, which is in the zeptojoule range, but that's still an area of active research. All of these magnetic logic devices that are being researched now would benefit from magnetoelectric switching as well as this biaxial anisotropy that I just introduced. And looks like we've got piece parts coming together, magnetic logic devices with magnetoelectric switching, spin-based interconnect. So now this field is in a very exciting time when there's a lot of fertile ground being plowed and a lot of new ideas coming up. And so I'm kind of bullish and excited about the ultimate prospects for magnetic computing. And let me end with just acknowledgments of the students in my group. I talked a bit about Brian Lamson, but I've got several other bright students and postdocs. I collaborate closely with Saif Salahuddin and Ramamurthy Ramesh with additional help from the IBM group of Stuart Parkin and the X-ray microscopy help that we get from Lawrence Berkeley Lab. And lastly, I just want to acknowledge sponsors. So thank you, and I'll be happy to take questions.
I'd like to ask for questions, please.
I'm just wondering whether you have looked at the injection. You showed the silicon and the graphene has a good diffusion length, but have you looked at the polarization after injection from ferromagnet to semiconductor or graphene? Because the polarization is going to downgrade, and then you're not going to flip the magnet by time.
So that's an excellent question. The question was, well, what are some of the practicalities of injecting spins into semiconductors like silicon or graphene? We need a tunnel barrier for silicon, which has a high resistance. which is a point that even bothers me even more. So the amount of I squared R energy dissipation to inject into silicon is pretty high. So that's a problem. And although I think the injection efficiency can be, in principle, could probably be improved to the point of you could get the device to work. But the energy dissipation would be pretty tough. Graphene has the same problem, although we've seen experimental reports of spin injection and spin transport in graphene without tunnel barriers, but the actual contact resistance for those devices, for example, cobalt on graphene, is also quite high, much higher than for metallic ferromagnet injection into normal metal like copper, which is really a honest low resistance metal-to-metal contact. So you're right in pointing out that those materials will require a little bit more in the way of innovation to figure out how to use them for this application.
A point on the magnetoelectric switching, which is so fascinating. What is the lowest voltage that you visualized for magnetoelectric switching?
So we're talking about voltages in the range of 100 millivolts or perhaps a bit lower, but right around that range. That's where we get to the attojoule kind of energy.
In regards to the magneto switching with the bismuth iron oxide, does that also follow this idea that a number of charges is required to charge up that capacitance, and does that also scale along with a regular transistor?
So it's a great question. We think that there's an opportunity here to do a little bit better. Remember, the charge on the capacitor that was needed to switch a MOSFET had to do with the slope of the switching. That is, the energy to charge up a capacitor to distinguish between 0 and 1 can be much less, as has been has been pointed out to me many times by Eli. In the case of the BFO switching, we're again taking advantage of a collective phenomenon, which is the ferroelectricity. So we think that we can do better than NKT, where N's the number of electrons on the gate of the capacitor. But the trade-off there, again, is that the ferroelectricity is also relatively stiff and probably involves around a timescale of similar to the magnet switching, which I neglected to mention, that the fastest that you, at least as we currently understand it, might expect to flip a magnet is probably dominated by sort of the issues of magnetic precession and the resonant frequency of that. So we're typically talking about 100 picoseconds as the sort of timescale to flip a magnet, or the ferroelectric. Although both of the ferroelectric switching speed needs a little bit more experimental investigation.
Okay, I think we should thank Jeff and go to the break.